the record button. Okay, so one quick topic before we go on to the main topics today. So scaling and shifting functions, this comes in handy for this week's exercise as well, so how to make it a bit less hairy to differentiate. So scaling is simple, so if you want to make a function higher, for example, this week we had time here, and we had distance here, and so the x isn't now on the horizontal axis, and we use the function that naturally goes to 1, and in this case it went to 5. So if we have some t1 here, and naturally if t1 is 1, then something should be 5. Well, our mystery function is simple as we put the multiplier in front of the function. So 5 t1 is 5 times 1, which is 5. So that's one way you can scale in that direction functions. Another way is that if we have a function, for example, somehow we have made a function that I need to find one of those ones. So let's say you have the opposite case. Strictly speaking, this is not a function now because it's, well, yeah, actually yes, it is. It does have a limit domain. So some function that goes this way. So it has an asymptote here at, let's say 1, and we would rather want to have, so if this is now ft, and we would like it to instead go to, let's say, not t1, let's call it 2 to have a concrete number. How do you do that? Well, the ratio between those, so now if t half would need to be at t1, and t1 would need, and so t equals half value would be at 1, t equals 1 would be at 2. So now we're gonna do this function here. Where's the rest of my markers? There it is. I'm gonna want to draw it on a different color. It already is kind of messy enough. So this function 10, which is intended to be the same shape, would be 10 f t over 2. So dividing that or putting a multiplier on the t, then just stretch it sideways. Adding something then can shift it. So what we had here on the example is that we wanted to have the function moved. So we want to have the same function, but maybe we want it to go from 1 to 2. Then here we have f t minus 1. So it moves it sideways by 1 unit. So those are pretty common tricks. And when you recognize this, how it matters with our exercises this week was that we had a function that is 5 times 1 plus e minus t plus 5, t plus 6. So this is effectively something that scaled 5 times up and shifted 5 units to the right. So if we look at this here, the 5 times 1 plus e minus t minus 6. Sideways shifting doesn't change what it is, and also we can take the common constants out of the both the derivative sign and out of the. So if we have, by definition, if we have ddx some constant times fx, we can do it some constant times dx fx, so we can do that on that side, and we can also do it on integral. So if we are integral of c fx dx, that's the same as c times integral of fx dx. So we can take constant out, which simplifies our calculations. And then on the shifts, well, how many of you remember on integration the substitution method? Okay, 1, 2. This is the chain rule. Essentially is the opposite of substitution method. So we could apply here the chain rule. So if we want to instead divide that into, well, the 5 goes out anyway, so we still need to integrate a sigmoid function with the t minus 6 as a parameter. Well, composite function differential is f dash g times g dash, and in this case, when our g is t minus or plus some constant, g dash is 1. So this is how we explain it with the chain rule. So when g dash is 1, we can ignore that. So when we shift with a constant, then we can ignore the g dash there, and we can now see that we could put whatever. Well, we could put just a blank variable in there, and then when we're done, we can substitute the internal function. So it always. So what we actually need to differentiate in that exercise is 1 over 1 plus e minus t. And then just remember that well, maybe something like t star. And then remember t star is really t minus 6. And then put a multiplier on it. So this is a lot easier to differentiate and then scale it back than using the wall formula. Well, not a lot easier, but there's less to write, and then there's less room to make small mistakes in writing. How do we explain that? So one other thing would be considered how large is this differential. So this dt here is some small change in our variable. And now if we consider then what is the differential for t minus 6? Then this shift for d2 ends up being the same. So dt over, now I use dt star, when we know that it is d over dt, t star is t minus 6, and equals, okay, differential of 6 is nothing, and differential of t is 1. So when we have the result that dt over dt star equals 1, that means that our differentiation unit is the same. But we'll have more about this later when we go through the substitution method. So this also shows that we can shift the function sideways without affecting differentiation or integration, as long as we remember if we're having limits or domains or specific region we do it, then we'll need to remember to take care that we're using the right units for the area of integration. Okay, and then we can get to what we're supposed to talk here. So let's talk a little bit about logarithms. Next question is, do I have my computer open? I do. And do I have my slides open? I do not, but that's relatively quick to find. And also it's now quarter past, so if someone was coming quarter past, hopefully you are here teaching mathematics. Mathematics. This isn't yet on the Moodle. Let's see, we got. Where's my just zoom in and share screen? Let's put duplicate one. Okay. And our no HTML1. So guess what? That thing isn't on. That should have come on when I used the thing here at the desk. Is this HDMI2? Is it connected anywhere? Yes. I'll need to fiddle a little bit with the control of this room because this thing has crashed again. So, okay, is it rebooting now? Is it rebooting now? What a wonderful room. To be creative to audio and video equipment. Okay, now this has power on. Power off. Okay, on please. Oh, now stuff is starting to come online. At least now I know how to reset this thing. And we should see some kind of an image soonish. Yeah, almost. Okay, now the next thing to do is to fiddle with the lights and figure out what lights I need to turn off to actually see anything. Okay, this thing dims all the lights. What's this button? Do some more. Okay, well, we can at least now see the slides that, so one usage, common usage for logarithms that I already hinted earlier is having some kind of exponential model. One of such thing is in metal cutting, if we need to optimize manufacturing time in machining processes like other wear processes and such that has the same issue. Okay, one thing is that we may want to consider: do we want the lowest price or the fastest production we can achieve? Those typically are mutually exclusive. So while if we produce really fast the batch, well, we will probably have as long as we don't need to hire new staff, the staff costs are maybe lower, but wear and tear on the machines is going to be higher. So for one batch of something we produce, we have the non-producing time. So so if TL is the setting time, so how much it takes to load and unload parts into the machine, or some other things that we need to handle parts, and then NB is the number of products made in one batch, then machining time or working time, so number of products again, times working time, and then we're having tool change time, so how many tool changes is the NT, or how many times we need to service things, or how many setups we need to do for that product. So if we need to configure our equipment, then we do have that kind of estimate, and then we get the CPR function, cost of production. So our tool changes, so the total tool changes are averaged over the average production cost, yeah, not the total. So for each part, we do have on the tool changes, it's divided for each part times the price of the part here on the right, and then CT was the cost of the materials. No, cost of the tools, yeah. So that last part is about how much time, yeah. So cost of the M is the cost of time. So how much does it cost? The last two terms are how much time does it cost? So running cost, how much does it cost to have the tools changed, and then CT is the cost of tools, so how much did the tools cost, or other things like that. And then we have the non-working time and the working time, and M is our costs over time, and that forms the total cost, roughly, plus materials. Materials don't seem to be in this equation. Lowest price, okay. So including non-production costs, then we can expand the formula. So now it is taking into account a model of how many tool changes we need to do, and we have this TR is the reference time for tool life. VR is the reference speed for cutting, and K is roughly the amount of material we need to remove. Or you could do the same formula for additive manufacturing as well. So how much material we need to add, and then you just have the speed of adding the material, but it does change slightly, but similar construction, and then the rest is common terms. And we'll next have a look how this monstrosity after the MTL plus MK divided by V is constructed. So there might be also tool sharpened costs. And if there would be no overhead, then we would have this minimal cost there. But let's have a look how we get those what we have on the minimal side. So how do we get it? So on the lowest part of this slide, how do we get this MK over 1 minus n VR TC over TR to the power of n? So typically, things like this are calculated. So it is a curve of if we increase cutting speed here on the horizontal axis, then what is the tool life, which is on the vertical axis, and this is an exponential curve that approaches 0 as cutting speed approaches infinity, and the hexagonal curve means how much play we have here under the curve to select our parameters. And the C, typically in these formulas, is a reference time of what's the speed, so that the tool lasts for 1 minute or maybe 15 minutes, depends on those. And alpha is a factor telling the slope of this curve. Same is a higher wear resistant tool of even material. HSS is high speed steel, so basic tool steel. And cemented modern tool steel. And cemented carbide is then a really hard material. So we are having a higher reference speed of 400 meters per minute there already. And alpha does change accordingly. So we have the larger the alpha, the larger reference speed exponentially. And with ceramic tools, okay, we might have something. So ceramics are really, the harder the tool, the more wear resistant it is, but the more brittle it is. So it doesn't take impact as well. So how do we do that? These tools, if we put a logarithmic, so those are exponential ones. So if we put in a log the coordinate system, those exponential functions end up being straight lines. Well, in this case, log because we have tensile strength of the material on the horizontal axis. So if we do material testing, we might end up needing this kind of a models. It's called Taylor's equation as well. And that's because of this guy who first started studying on the scientific production, also occasionally known as Taylorism or Taylorian methods of measuring production times and then doing modifications and figuring out several things like what we didn't really, for example, using of coolant in metal cutting ends up getting more productivity, something that we didn't know a little over 100 years ago before Taylor studied that. His magnum opus is the On the Art of Cutting Metals, which was published in 1906 by American Society of Mechanical Engineers. Different wear mechanisms may cause also changes on the slope. So if we have more speed and V, we're having more heat. And this is also where the last exercises we had this calculation of the friction vector. Then the amount of friction we get essentially causes more wear, because higher heat makes the material softer, typically the tool material softer, and then the tool starts to wear more. But then on low feed we're having temperature increase on a different phase, and then so we need to optimize it up in the real world case. Usually we optimize it for flank wear, so for speed. But if we go too low, there are then other concerns that cause trouble in the manufacturing. There's a standard which says that our tools are broken if it fractured, so it just blows apart, or then we're having flank wear or average flank wear, or then we're having maximum flank wear, so kind of a crack there. And the sintered tool, which is one of those ceramic carbide tools, is broken similar conditions. So if we're having craters, or we're having this flank wear again. So what does it look like? So here's the image looking at the edge of the tool on the right. So this VB is the average wear of how much of the corner has been shaven off, and VB max is the depth of the highest part on the B zone. So how much is the maximum wear on the zone B is the VB max. And then we might also consider what happens in the corner, which is zone C, and then the zone M is then further away. So something probably wrong if we're having zone M wear. And a crater, so the very right on top image is from the top. So if we're having a crater on the face there, so which is towards the cutting direction, then it's crater wear, and we may also need to consider depth of the crater. And how to model it? Well, okay, one more. So actually, it is just a part of the wall model. So in some parts, if we are going too low, there may be just built up edge means that we're having material that doesn't flow properly on the tool, and it gets welded on the tool. That causes trouble as well. So we're having troubles there. But then when we're on the proper cutting parameters, then roughly on that area we can estimate the wear with the previous equation, which has a simplified form of something like that. So now we do, it was a straight line on a log part, so cutting speeds and tool life should form a straight line. So we'll do a couple of measurements and fit that line there. And for fitting straight lines, we do have, ideally we could, if we're having really good doing the measurements, we could do it in 2 tries, and everyone knows how, if you have 2 points, how to draw a line so it passes through these 2 points. That's the simplest way we could do it. And then how to get those parameters out of this. Essentially, the equation ends us looking like this. So cutting speed and tool life to the power of alpha is some constant c. And these are the alpha and c that were referred to in the earlier slides. So cutting speed, tool life for given wear condition, tailored exponents, and cutting speed for tool life of 1 minute. So on the log coordinates, alpha here is just the slope of that equation. and then you can, when you know t to the power of alpha, then you can solve what is c when you know at least one of the points of the cutting speed. And that's one application where we might run into logarithms. So here we could directly fit the exponential model. So we can trade easier model fitting for a bit more calculations on the data, for essentially taking logarithms out of both axes. So, and then I've noticed that a lot of us use computers. So next week I had an idea of doing a little bit on numerical differentiation and numerical integration. So we'll have one preparatory topic today. It's already on the week 4, but we'll have a look at how computers store numbers. There is now I can't remember what it is in English. In Latin we would say pons asinorum or aasinsiltain in Finnish. So there's a distant connection also to this week's exercise number 3, which had those constants we had were powers of 2, and you can do easy common factorization with if you have different powers of 2. So actually I'm going to stop the screen share for a moment so I can hop on to the whiteboard. So we remember that if we have the same root here, then if we have whatever constants here, this is same as a the power of b plus c. So that way it's relatively easy to get, if you have those power 2, it's relatively easy to factor those. So for example, we had 16, which is 2 to the power 4, and 256, which is 2 to the power 8, and which is also 2 to the power 4 times 2 to the power 4. So we can clearly see that there's a common factor of 16 there. And hopefully I wasn't standing in front of the camera for people who are online. But let's go on. So how computers store numbers? So the basic number we have in a computer, more or less all computers, is an integer. So whole numbers, so made out of bits. But we do have also other ways to estimate, not have accurate representations of real numbers, but we can have some kind of a decimal estimation of real numbers as well. So a lot of calculations these days are done on computers, and there are a few ways that the storage of numbers affects what happens on those computers. And we do consider integers, real numbers, and then also a special case on characters, or basically, which usually stand for letters, but all letters do have a numerical estimation as well. There goes the camera. Oops. But we won't be needing this anymore. Hopefully, and no one was actually looking at the camera part, because actually the camera feed will be recorded. So I don't know. Let's try to still keep it pointing on the whiteboard. Yeah. Now let's see what those terms mean. Basic, so everything gets stored as bits, which is usually marked with a lowercase b. So occasionally people confuse bit with a byte. So byte is typically 8 bits. So one bit has two possible values, usually representing 1 and 0. The real storage of a byte usually is not 1 and 0, but it's either some kind of voltage values. So there is I should have checked 4 and up something volts, 4.8 volts is 1, and 0 volts is 0, but values in slightly above are, so there is a tolerance zone, and then there is a forbidden zone. If there's a voltage value somewhere in the middle, it's kind of undecided which one it is. But there are other alternatives. If you have seen a CD compact disc, then the storage uses a slightly different system. So there's a different kind of a reflective surface when bits swap from one to the other. A byte is usually 8 bits, and then word is a term that refers to usually the memory bus size. So how many bits are transferred at once. So 64-bit computer can transfer in one clock cycle. It works in a kind of a turn-based manner. In one clock cycle, it usually can transfer 64 bits of information. And so if we're having an operation that can be done in 4 clock cycles, then on a 4 gigahertz processor, it's, well, giga is a billion, so it can do billion operations for 64-bit numbers per second. And then we have, so integers can be stored in those bytes. It's also occasionally called octet because it's 8 bits, or occasionally also character because it also happens to be something that we usually store. So 256 different characters can be stored in 1 byte. So there are options. And if we need to represent more than 256 characters, then we either need to do character maps. So for example, in the old days, different languages that had special signs had different mappings of what number in that byte meant what character. So if you type Finnish, which is characters with dots on them, and read that file on an English computer, it might have some kind of weird brackets instead. They are possible to have unsigned and signed values. So those integers do vary whether or not we need to have negative ones. So if it's unsigned, it's usually 0 to 255. So all zeros means that the value is 0. And then if we need to have signed, then we'll see soon how it works. Short integer is typically 2 bytes. So we call it int16, and then similarly uint16 for unsigned and just int16 for signed ones. And long, then okay, some computers have this long or huge or whatever name for the 64 bits and so on. Occasionally there might be also enumerated lists, so we have a definition of what binary value refers to what kind of a number. We mostly do not do any kind of a really low levels of binary hacking stuff here, but some of these things are good to know. For example, if you're using integers and you have 255 and you add 1, why do you get 0? Or if you have signed integers, you have 125 and add 5, then it would be with 130, but it ends up being minus 125 because it will roll over to the other side. In some cases, it's useful to know if your machine is big endian or little endian, so in which order are the bits saved, whether it's like we write regular Arabic numbers so that the most significant bit is on the left, or most significant numeral, and the least significant, so the ones are on the right. So yeah, in some languages, just all the details are just kind of going away, and we just use the language without ever needing to know how it's stored, as long as there are no bugs related to it. So abstraction is hiding the details in this case, and we're also one reason why we want to use functions and occasional symbols, so we don't need to keep the values with us. And so higher level means higher amounts of abstraction, and lower level means that we are closer to how the electronics actually work. Limitations. So yeah, if we have an unsigned integer of 8 bits and add 1 to 7, we'll get overflow and it rolls up to 0. Same with the unsigned integers. 255 plus 1 is, sorry, minus 128 on the signed one, of course. On the unsigned ones, then we don't go to 256, we go to 0. Similarly, we can do it other ways. So if we have the signed one and have minus 128 and deduct 1, it rolls over to 127. And then if we subtract, have unsigned one and go to negative numbers, it rolls over to the top. And in some cases, it's also necessary to know what happens when we have a non-integer result. So then we're having a real number which we need to represent as an integer. Typically, for most languages that I've used, the type is truncated, so it essentially calculates the value until the decimal point and then ignores the rest. So always rounds down. Now I think about negative numbers. Does that actually happen? Or does it round? Yeah, it does always round down. And MATLAB does the correct rounding, so it uses a few computing cycles more to figure out if the remainder is closer to which integer and round to the nearest integer. So that does also happen. Real numbers, we don't really store the real numbers. What we store an approximation of the real number using by something called floating point numbers. So what that means is that we essentially use a kind of a version of the scientific notation to store numbers. So we have some value of the number times the significant times the base to the power of the exponent. Sorry, the significant is the value or the closest kind of a decimal approximation of it, and then the base to the power of the exponent tells essentially the position of the decimal point. There could be others, but the standard one is always base 10. So, well, this significant will be a binary number, but the base for the assigned notation will be base 10. So, for example, 1.0001 will have the value of 10,001 stored as a significant, and then it stores -4 as the exponent. And that's a representation of that number. And the floating point means that if we need to go higher up one kind of a degree of magnitude, then we can just increase the exponent. So the decimal point location in the significand, so in this number, is not fixed to same location, when we can change it as needed. And the exponent is stored as an unsigned integer, so integer exponents only, but it doesn't start from 0. So single precision one has 32 bits, which is 4 bytes in it. One of them is the sign, so this has a separate bit for the sign of the number. 8 exponent bits from -126 to 127. So this is not the same range as our unsigned integers, signed integers. And there are some special values. So if the exponent is all zeros, it tells that we're having either 0 stored, or then we're having a subnormal. So if it's all zeros, then it's 0 as a value, but it might have something called a subnormal value. And if it's all ones, it's infinities or natural numbers. So in floating point mathematics, we can store infinity, plus and minus infinity as a value. And the significand is 23 bits, but it's a special rule that it cannot, if this exponent bit isn't all zeros, it is not 0, so it will have one more bit of precision there by the deduction. And the range is from relatively large numbers, but there is a thing called underflow. So if we try to model really small changes within that range, we will round to the nearest presentable number, because we don't have an infinite number of decimals there. We have only 23 bits for the significance. So we have 23 bits of significance available. Double precision is the same, but we have more bits. And double precision is, by the way, the default type for MATLAB if you're using MATLAB for something. Usually double precision is, well, at least when I was trained to program, it wasn't really your first pick, only when you needed it to be extra careful on values. But when we have more memory, then okay, that's so single precision is also called float, and double precision is called double. So, but if there's enough memory, well, maybe you could use those. Okay, then we have underflow. Yeah, unlike real numbers, they aren't arbitrarily accurate. So when we're trying to get too close to 0, we're getting underflow. That's a proper definition there. 0 is defined, so if we are all zeros, but then the sign bit is still applying. So if we're having really close to 0, we can still tell that are we above or under the 0. So we do have +0 and -0 in floating point numbers. And then if we're somewhere between two representable numbers, then we're having rounding, and then there's also the possibility of subnormal numbers. So what happens, we're closer than the actual closest value to 0 we can represent. Then we can start actually putting leading zeros onto significand. So we're reducing accuracy to be able to display smaller numbers. Hopefully you won't run into this, but one way we can run into this is if we have a really large number, or we represent as a floating point, and we add a really small number to it. For example, if we do numerical integration, so we calculate in small slices and are summed that far, so we do it iteratively, piece by piece. Then when we have a really large number already as the integral value and we add a really small number to that, then it rounds back to whatever it was. So we're essentially adding nothing to it. So that is probably one possible error you may run into. There's also a possibility of using fixed point math. Consider the international system of units. So essentially we tell that, okay, we use integers, but this integer is actually having a unit of 1,000 parts, for example. So we shift using integers, but then the ones represent actually the, for example, 1,000 parts. This improves speed compared to floating point numbers because integer math is way faster than floating point math to calculate for electronics underneath, but we are going to lose some precision. And arrays, okay. So when we represent a vector or a list of numbers, there are different ways of storing it. Usually it's just a block of bytes. So we have defined that this area in memory represents this kind of array. There are different ways of saying what is what. So the first member might be, or the zeroth member might have in storage that how many numbers we need to store, or others start having the actual value starting from the first one as well, and then require a specific null sign that tells that, okay, here's where it ends. And yeah, we do occasionally have that the beginning of the array is the zeroth member. This has to use some uses on because, for example, in binary form, the ones place is, or that in that kind of if we do base conversions, then the ones place is the base to the power of 0. That ends up being always 1. So how many ones might be on the first spot, for example. Some languages start also referring that the first number in the list or vector array is the first component. And also things like if we have a pointer in the memory, then so if we are referring to the variable in the hardware memory by its address, then a 0. So if then in that kind of case we can refer to any location in the list if it starts from 0. So first member is 0, then that's the beginning address plus 0 times the size of what we're storing in it. Second one, if we add one size of whatever we have stored it, then the memory location of that is the beginning address plus 1 unit and so on. So that's also one good part for using this 0 indexing. You're going to have C language as your programming language on your programming courses, and C language works like this, so it's relatively close to low level. So in C, if you have a reference to a table, it actually refers to the starting address of the table. Text, it's also saved as a number. Do I have MATLAB open here? So I don't, but it's relatively fast to open. So at least if I'm on the internal network. So there may be different types. So one way is that we tell that this part of memory refers to a text string, and one way, the classic way, is that it is a table of characters, so values which correspond to some numbers. In MATLAB, it works like that if we're having letter in single quotes, it's going to store it as a character array. What happens if I add number 1 to this letter? Okay, 98. Because the numerical value of the letter A when stored in memory is 97. So we could have alphabet, which in this form is A, B, C, D, E, F, G, H, and so on. And they do have a numerical value. I'm not going to have +0 just to get them to show. So it starts from 65, 66, and so on. So that range of numbers can also be represented as letters. And the rest just jump because I wrote and so on. However, if I store it as a string, so Merkiono is in Finnish the same as string, but string is a reserved word. That's why I can't use it. Here's A, B, C, D, E, F, G, and so on. If I add 1, it adds 1 on the end of it, so it does different kind of representation what we're doing. Difference is in this language we represent these strings with double quotes. In C we need to define the data type, so then it doesn't have this kind of a same thing. But for example, if you ever work web pages, then JavaScript has well, it tries to guess what you're typing, so then it has a bit of issues with that as well. This was optional last year, but let's have a quick look. So converting from base 10 to base 2, find the largest number, which is smaller than equal to number we're converting. Take a note of what the exponent was and then reduce that number, and you get what's the remainder, and keep on going until the remainder is 0. So for example, if we want to convert 14 in base 10 to base 2, well, the largest base 2 number we can get, 16 is too large, so 2 to the power of 3 is 8. Okay, that's okay. We mark the third bit. So now we're 0 indexing, by the way. We mark the third bit. It's 8. We reduce 8 from 14. The remainder is 6. Largest, well, 2 to the power of 2 is 4. Smaller than 6, mark bit 2. We get 2, which is 2 to the power of 1. And then we're done because the remainder is 0. And what we get is bit 3, 2, and 1 are 1, and bit 0 is 0, so we get 1110 as the value. Relatively simple. And then the other way, it's even easier. Check what bits are 1, and then note which these are. So reading from right to left, the 0 bit is 1, first no, second no, third, fourth 1, fifth no, sixth and seventh are 1s. And then calculate the power of 2 and sum those up, we get 2017 in base 10. From any base to any base, then kind of a similar, except that now we also need to, when there are multiples of something, we need to check how many multiples we can add. So it's not just checking the highest power, but also the highest power that below the remainder might fit several times. So we're gonna convert 16 in base 12 to base 3. That's 10 in base 12 plus 6 in base 12 to use the divide and conquer approach. So always, if you have a harder problem, divide it into easier parts. And we have 3 to the power 2 plus 2 to the power 1 that fits there. So we get 1103. And the 6 of 12 parts, it's 2 times 3 to the power of 1, which we represent as 2O in base 3. And then 110 base 3 plus 2O base 3, we're having 130 base 3, but okay, 3, we cannot represent 3 in base 3, so it overflows, so it's then the first number becomes 2, so we have 200 base 3. And yes, that's not 200, that's 2 times 3 to the power of 2. Subtraction with binary. Okay, we can represent 12 as 1100. We can represent 5 as 0101. And when we subtract these from each other, starting in zeros place, 0 minus 1, carry 1. Okay, that's 0, so carry 1 from the 2 to the power of 2's place. We have, and we can calculate that, so that's 1, 1. Then we still have this 0100 to subtract, and then we get that. Also, we need to carry again from the to the power of 3's place when we get 0111 as the value. So that's just need to remember that when you reach the base number, then you need to start carrying. That's the same in our decimal representation, but of course, when we in decimal represent 10 as 2 numbers, then it becomes kind of the way we write numbers regularly. Subtraction, now we're doing signed numbers. It's the same, but then now we're subtracting a larger number from a smaller number, so we go negative. And how it works under the hood is that the lower part of the range is working as regular, and then the higher part of the range does represent the negative numbers. And when we do it this way, then we can use the same algorithm with signed numbers as we can with unsigned numbers, and we don't need to have separate algorithm in the computers. So the algorithm itself doesn't care about the sign when you're using standard binary integers. And then one nice trick, when we're having octal or hexadecimal numbers, we can cut based on certain groups. So if we start in binary, then we can cut based on what the base is in the binary system. So octal numbers is 2 to the power of 3 is 8. We can convert these in sets of 3 instead of converting entire huge number at once. So 111 is 7, and 000 in binary is 0. So this is 70 into octal system. We can convert piecewise. Similarly, hexadecimal numbers, so base 16, which is relatively common, 111 is F, 000 is 0, and it's F0 in base 16. Also, there are occasional tricks in base 16, like storing a number, which if you view it in hexadecimal, reads something like cut feed or dead beef or something like that. It's then if you're reading some dump in binary and have the hexadecimal conversion, it's easy to spot a word in the usual jumble of values. And that's it for today. Next week, we'll see how we can use computers to differentiate and integrate. If anyone has still questions on our exercises, do ask. Well, anyway, stop.